Okay, so this is now the P3 review for you, which is a lot of calculations in here, and then it also goes into car safety and then also the roller coasters. So the first part of this topic is again using one of those calculations off page 2. In this case, it's to calculate the speed. So speed, quite simply, is just your distance divided by the time. So obviously, again, because we've got those three parts, we can put this into a triangle so that should you be asked to calculate the distance or the time, then you can rearrange the equation nice and simply. Now, there are two types of graph that you need to understand in the P3 topic, and the first one of these is the distance time graph. Now, what we can see on the graph here is that there are three different coloured lines for you to look at. So if we look at the green line first of all, what we can see there is this straight diagonal line that's going to be quite a steep incline, as you can see. Now, what this tells us is that it's a steady speed. Any kind of straight line is a steady speed, okay? Now, because we've got quite a steep gradient on this one, then we know it's travelling very quickly. So what we have is actually an object that is travelling at a fast, steady speed. Now, if we have a look at the blue line next, that curved line, then what we can see there is an object that is accelerating. It's getting faster. So we have this curve on the line because our time is increasing at different rates to the distance. Then finally, that red line on our graph, this one is showing three different points. So the first part of the graph there, so the first three squares, for example, that's just showing you that it's travelling at a steady speed, but at a much slower speed than the green line itself. If we have a look at the next part of the line, squares 4, 5, 6, and 7, then we can see it's this flat horizontal line. Now in this instance we can see time is increasing while distance is not, so we know that our object is stationary in that instance. The last part of the graph there, where it's sloping back down towards the timeline, what's happening there is our object is returning to the start. So what we can see is time is increasing, but distance is decreasing. So obviously that object is going back to where it began. The only other point to note about our little distance time graph here is that when we're looking at the actual gradient of our line, then we can actually work out the speed from that. So we mentioned acceleration on our previous slide in regards to that blue curved line. Now, when we're talking about the acceleration of an object, what we're talking about is how quickly your speed is actually changing. So again, on page 2 of the exam booklet, you will find this equation here. So to work out the acceleration of an object, we're looking at the change in speed divided by the time taken. So again, go careful when you are calculating this one to make sure that you do work out the change in speed first of all. So do not just look at, say, the final speed. Always work out how much that speed has changed. Then divide it by the time taken to give you the acceleration of that object. So the second type of graph that we come into contact with here is the speed time graph. So what we can see again when we look at the graph on my slide is that we've got two different coloured lines in this instance. So if we look at our blue line first of all, it is just that straight diagonal line. So what we can see there is that as the time increases, the velocity also increases, and they're in proportion. So what we have there is a constant acceleration. Now if we look at our red line, then what we can see is again that first part of that red line there is showing a constant acceleration, just at a slower rate than our blue line. When we hit that top plateau, that flat point, then we have a constant velocity. Time is increasing, but the velocity on that y-axis is staying the same. So our object is moving at a steady speed here. Then finally, that last part of our red line, we can see that our object is decelerating, because as the time increases, the velocity is decreasing. So again, make sure you look carefully at the axes on this graph, okay? The kind of question they're likely to ask you could very well be they'll give you a selection of speed time and distance time graphs and then ask you which one shows a certain feature. So in order to work that out, the first thing you've got to do is look at the x and y axis to work out whether it's a speed time graph you're looking at or a distance time graph that you're looking at. So do go careful there to make sure that you look at the axes first. Now, with regards to our speed time graphs, if we're talking about the gradient in this case, we're talking about the acceleration of our object. If they ever asked you to calculate the distance that an object travelled, all you would actually do is work out the area underneath the graph. So if we were asked to calculate the distance the red object had travelled, then what we actually do there is divide it up into 3 sections. So we divide it up into the 2 triangles and a rectangle in that central section. Calculate the areas as you're taught in maths, and then just add them all together to get the total distance travelled. So we then come on to thinking about gravity. Now, when we're talking about gravity, we're talking about the force of attraction that occurs between all objects. So if we're looking at gravity on a planet, it's what makes all objects accelerate to the ground at that same acceleration. Now that's given this sort of term g, okay? So if we think about Earth, then g is equal to 10 meters per second squared. So what we say is that every object on Earth will accelerate towards the ground at 10 meters per second squared, okay? You don't have to remember that value for g though, okay? Just understand what it actually is talking about. Now, there are 2 definitions here that you should have learnt lower down the school, but do go over them to make sure you know what they are, which is mass and weight. So if we're talking about the mass of something, this is what it is in kilograms. So it's quite simply the amount of stuff that something is made from, okay? Whereas if we're referring to the weight of an object, it's actually a force. So that means that the units for it will be newtons here. So it's actually the force of gravity acting on that mass. So if you wanted to calculate the weight, quite simply, all we'd need to do is the mass multiplied by that gravitational field strength. So for example, if we had a person who weighed 60 kilograms and they're on Earth, if we wanted to calculate their weight, it would be 60 times 10, which is the gravitational field strength on Earth, which would give them a weight of 600 newtons. So just a little recap on different types of forces that are involved, okay? So you've got gravity or weight. Now, those two both act in the same direction. They both act down towards the surface of the Earth, okay? So if you're asked to label on the names of forces onto a diagram, the one pointing down will be either gravity or weight. Both is acceptable as an answer. You've also got the reaction force, which is, say, the force that's acting against you as you're sitting on the stool, okay? So that's pushing up against you on that stool or as you're standing on the ground. You've obviously got the thrust, which is the driving force pushing the direction of movement, pushes and pulls. Hopefully you know the difference between them. The other one we've got that's very important in terms of our exam questions is our 4th point here, okay? The drag, the air resistance or friction. Now these all act in the opposite direction to the movement. So if we had a skydiver, for example, then we would have gravity or weight pointing down towards the surface of the Earth, and then we could have drag or air resistance or friction acting up against it. So what we see is there is this opposite effect, okay? So you've also got lift and also tension. There's 2 other forces, but they're less likely to come up on your exam paper. So just to recap what we did back in year 7 when we looked at forces, those 2 patterns that we see. If the forces acting on an object are balanced, i.e. they are the same, then our object will keep moving at the same speed. So if it was moving at 30 miles an hour, it keeps moving at 30 miles an hour. If it was stationary, it remains stationary. The other side to that is if we unbalance those forces, then our object will change speed or change direction. Now, the actual effect there is going to depend on where that greater force is acting. So again, just look carefully at your question and think, if the greater force is acting in that particular direction, what effect will that have on my object? So friction then, this is again something we did a lot of work on going back to Key Stage 3. Now when we're talking about friction, its important part is that it's going to slow objects down. So we actually use this in a lot of different applications to bring things to a stop. So things like brakes, for example, it's using friction. So we actually have our friction occurring in 3 different ways. First way is between 2 solid surfaces which are gripping each other. The second way is between solid surfaces which are sliding past each other. And the third way is in that resistance or drag from fluids. Now remember, fluids can either be liquids or gases. Now we do see a little bit of a pattern here in the terms of what will increase friction for us. So we see an increase in friction when the speed of our object increases, or when we've got a greater surface area. Now obviously we'll be applying that in terms of a parachutist, because as they jump out of the plane they're obviously travelling very quickly, and in order to slow them down we need to increase the amount of friction acting on that person. So what we do is, by opening the parachute, we increase the surface area and therefore increase the amount of friction. So the next term we come across is this one, terminal speed. Now this is generally applied to someone jumping out of a plane. Now what we're talking about here is, if you imagine someone jumps out of a plane, then at that first point, just after they've left the plane, they're going to be accelerating. Because what we find is there is a greater force acting down towards the earth than there is acting against them, going back up, if you like. So what we see there is, because the bigger force is acting down, then they accelerate towards the earth. So their speed is going to increase. Now, as we just said, when speed increases, then the amount of air resistance will also increase as a result. So what we then see is the acceleration is going to reduce. Now this keeps happening until we actually get to this point where our resistance is equal to the accelerating force. Now where that happens, that is our terminal speed. And our little skydiver is going to keep falling at that exact same speed until something changes. So in terms of our forces and acceleration, we've already looked at our patterns here. Okay, so the only bit that really needs to be considered is that equation at the bottom. Again, page 2 of your exam booklet, you'll find it printed there. So if you are asked to calculate the force acting on an object, then all we need to do is use the mass and the acceleration and multiply them together. Okay, so again, if you need to rearrange that equation, because it's only those 3 parts, we can put it into our triangle. So the next part of this topic was all about cars. Now, we do have this thing called a stopping distance. Now, when we're talking about the stopping distance, what we're actually referring to is the thinking distance plus the braking distance. So we need to understand what those two terms actually mean. So first of all, we'll have a look at our thinking distance. Now, quite simply, the definition for thinking distance is the distance travelled between recognising a hazard and applying the brakes. So go careful here, okay? Do not say it is the time taken. It is a thinking distance. So it will be the distance you travel between seeing that kid walking into the road and getting your foot onto the brake pedal, okay? Now, what we actually find is, one of the typical questions on this one, it'll ask you what the thinking distance is, and then it will ask you what will actually increase it. They might give you a table to tick boxes in, they might just ask you to recall. Now, what we find is our thinking distance then is going to be increased by things that affect you as the driver generally, okay? So the first one on there is the higher speed. Now, that's true of both thinking distance and braking distance. The others are purely the thinking distance that they affect. So if you are tired, if you have taken drugs, if you are drinking alcohol, if there are distractions in the car, if you're on your mobile phone, all of those will increase time it takes for you to recognise a hazard, and therefore it will increase the distance you travel between recognising that hazard and getting those brakes on. Now, our braking distance then is the distance taken to stop once the brakes have been applied. So when you've got your foot on the brake pedal, however far you travel until you come to a complete stop, that's your braking distance. Now, in terms of what increases your braking distance, it is generally to do with the condition of the roads and the car itself, okay? So we still have our higher speed in there, but then we come on to those other factors that are purely the braking distance that they affect. If we have a greater mass, for example, it will take longer to come to the stop. If you've got poor brakes, a poor road surface, poor weather, poor tyre condition, do go careful when you're actually writing one of these answers. Don't just put down brake condition, because if it's asked you what is going to increase the braking distance, you must use the word poor, okay? So do go careful not just put a generalised term and then lose those marks unnecessarily. So momentum was our next little topic then. So what we have here are two different calculations. Again, both of which are found on page 2 of your exam booklet. So our first one up here, to calculate the actual momentum, what we're going to do is the mass multiplied by the velocity of our object. So again, should we need to rearrange, it fits in our triangle method nice and simply. Now what we actually find is that what we see is a change in momentum is always going to be caused by forces acting on an object. So if we want to work out the forces acting on something, then what we do is our change in momentum, so go careful as it is another one of those changes, divided by the time it takes for that change to actually take place. So again, that one fits in our triangle should we need to rearrange it. So car safety was the next thing we really looked at here. Now what we're actually talking about are features that are going to be designed to reduce the force acting on people in an accident. Now the way that manufacturers actually achieve this is by increasing the time it actually takes to slow down those objects. So there were 3 examples that you needed to understand for this topic. You had crumple zones, seat belts and airbags. Now the way a crumple zone actually works is that should your car come into contact with something else, then it actually has a very controlled squashing of the front of the car. So what it actually does is it's going to give more time for that car to come to a stop because the front of the car is going to be crushed in. So that does reduce the force that acts on the people in the car should an accident occur. Seatbelts, if you've ever sort of moved forward in terms of quickly moving forward, then the seatbelt has that bit of give before it locks into place. Now it's that bit of give that's going to mean that you are slowing down, but it's taking a longer time to do it rather than being fixed right back against the seat. Then obviously the time is very small. And then finally our airbags again work in a similar way, that it's going to take you longer to come to that complete stop. So what we see here is they're all designed to increase the time it takes to slow the object down. Now ABS brakes are another form of safety feature in our cars. ABS just stands for anti-lock braking system. Now what these actually do is that they're going to stop the wheels from locking when you slam the brakes on. So what's going to happen here is if you put your foot heavy on the brake, then they don't just lock into place. Instead what they do is they're going to automatically pump on and off to prevent those wheels from locking and therefore prevent your car from going into a skid. So what we actually end up with here is a shortened braking distance, because what we'll have there is obviously this more controlled stop of our car. If you go into a skid, obviously you don't have control at that point. Now the whole idea of this is that it's going to hopefully prevent collisions. Back to another calculation at this point. This time we're looking at the work done. Now wherever we're referring to work, what we're actually talking about is a force that's moving an object. So if ever we wanted to calculate this, on page 2 of your exam booklet again, you will see this equation here, work done equals force times distance. And again, hopefully you recognise it's those 3 parts, so again we can rearrange it using our triangle method. So we then come on to different forms of energy. The first one we're going to look at is our gravitational potential energy, or GPE. Now what we actually have, GPE is caused by something being raised off the ground. The higher something is, the more GPE it has. Now if we wanted to calculate this, again found on page 2 of your exam booklet, we have this calculation here. Our GPE is the mass times G, which if you remember is specific to the different planets, times by the height. So again, all you need to do is read the question carefully, put those numbers into your calculator and get the correct answer. The other type of energy that goes hand in hand with our GPE is kinetic energy. Now this is the energy of movement. So if we wanted to calculate the amount of kinetic energy an object had, we would do 0.5 or half times the mass times by the speed squared. Okay. Now do go careful when you're using your calculators, because some of them have their own little quirks. It might be advisable to square the speed first, push your equals button, and then multiply that by the mass, and then multiply it by 0.5. Just go careful, because otherwise sometimes when you use your calculator you might end up doing the sums and then squaring your answer only. Okay, so do go careful there. There are 2 patterns that you should remember about our kinetic energy. The first one is that if we double the mass of our object, our kinetic energy will also double. Whereas if we double the speed, then it will quadruple. Now the reason for that is quite clearly in that equation, that if we double the speed, because we're squaring it, then our kinetic energy is going to quadruple. So do be wary of this one, because when we're talking about kinetic energy, obviously it could easily be linked into our cars in terms of accidents or just in terms of stopping distances. So if you're asked why the stopping distance increases with speed, then you can link it into the fact that it has more kinetic energy, and therefore that has to be dissipated before the car comes to a complete stop, which takes longer, and therefore the car will travel further. So we can apply this knowledge of gravitational potential energy and kinetic energy when we consider our roller coasters. So think back to when we went to Thorpe Park here, okay? What we saw there was this conversion between gravitational potential energy and kinetic energy at those different points of a roller coaster. Now the key thing to remember here is whatever kinetic energy we are gaining, it is the same as the amount of gravitational potential energy we've lost. So that gives us these two equations on the little PowerPoint slide here. Now obviously we know kinetic energy has the calculation half times the mass times the velocity squared, which is what we see on the left there. We know that gravitational potential energy is the calculation mass times g times the height. So if we know that our kinetic energy gained equals the gravitational potential energy lost, then we can say those two equations equal each other as well. Now, what we could actually be asked to do in one of our exam questions is to calculate the height of something, at which point we would use the equation at the bottom. Okay, so it will be the velocity squared divided by 2 times g. Okay, now that will give us the height of whatever it is we're looking at. Do learn that equation at the bottom, because they won't give it to you, and it will save you a lot of time in terms of rearranging equations, which isn't necessarily your strong point. So learn that equation at the bottom. You don't have to know many for the physics, because most of them are on page 2, but learn that one there to calculate the height. Our next calculation then is looking at power, which quite simply is the rate of doing work. So if we think about a very powerful machine, they're going to transfer a large amount of energy in a very short space of time. So if we're ever asked to calculate power, there are two equations that you can use, and obviously which one you actually use is determined by what the question actually says. So obviously our first one there to calculate power is the work done divided by the time taken. This could be a follow-on question from where you'd already worked out how much work is done by an object. So do look carefully to see what information you are given, and then you can select the correct equation. The other alternative for you to calculate power, it would be the force times by the speed. So you can see they are quite different in what they actually contain. So if you read the question carefully, underline the information in terms of what you are given in terms of numbers, then you should be able to identify which of the two calculations you are going to use in that instance. Now another consideration when we're talking about our cars is the fuel consumption. Now this quite simply is just how much fuel our car uses. Now what we normally see is that this is a value given as miles per gallon, or MPG. Now what we'll actually see is when we compare these fuel consumption figures for different cars, those that have a higher power engine, they have this higher fuel consumption as well. So what we will see is there are 5 things that actually determine the fuel consumption of a vehicle. First of all is the size of the engine. The bigger the engine, the higher its fuel consumption will be. How you actually drive your car will affect it. It's much better to have a nice smooth driving style rather than sort of starting, stopping and accelerating rapidly. The mass of your car will affect it. The greater the mass, the higher your fuel consumption. Your speed, so if you go very quickly, you generally burn more fuel. And finally, your road conditions as well. Okay, so all of those could affect how much fuel you are actually consuming per mile. So the final part of this topic then is just considering the fuels that different cars use. So what we have these days is most cars will run on fossil fuels, i.e. petrol or diesel. Now the key thing to remember here is they're both non-renewable fuels, and they both create quite a high amount of emissions. Now obviously the amount of emissions is going to vary from car to car, but they do create that carbon dioxide, the sulfur dioxide and so forth, which is going to lead to the problems of acid rain and global warming. So not the best solution. There are alternatives available to us though. One of those alternatives is to use these things called biofuels. Now these are made from plants or organic waste, and the big advantage here is, number one, they are renewable fuels. So that means that we can just keep replacing them when we use them. The second side to it is they're described as being carbon neutral. Now, if you imagine when plants are growing, they carry out photosynthesis. This means they're removing carbon dioxide from the atmosphere at this point. So that's then going to be stored inside our plant, and then when we burn it as our biofuel, it releases that same amount of carbon dioxide back into the atmosphere. So we're not generating any extra carbon dioxide, hence the term carbon neutral. The last example on there then is the electric car. The key thing to remember about this one is that while it won't make any pollution as you are actually driving the car around, we will be making pollution when we make the electricity. So the way these cars work is they've got a large battery inside them, which you plug into the mains to charge it up. So obviously mains electricity, we know, comes from power stations, and the vast majority of power stations in the United Kingdom are still fossil fuel power stations. So that's where we get our pollution in this instance. Now I hope that helps you out with P3. Obviously just remember to show all your workings with the calculations and make good use of page 2 for this particular topic.